Good morning, everyone. How are you? In the previous class, we have studied ray optics, some basic phenomena of plane mirror, reflection through a plane mirror, and a basic phenomena of refraction. That's all we have covered in the previous lecture. So today it's a part two, or in fact, we can say it's a final part of the ray optics. Be alert and be attentive. Pen and paper should be with you. And in fact, I would say must be with you. So let's start our today's session. Okay. So first topic that we are going to study here is critical angle. What is critical angle? Let's understand it. Let's suppose there are two mediums like this. One medium is mu1, another medium is mu2. Out of them, one is rarer and one is denser. Let's suppose mu1 is less than mu2. What does it mean that mu1 is rarer? Is my voice clear now? Just say yes or no at least once. Is my voice is audible? Okay. Very good. Now, let's consider a ray is entering like this. This is the incident ray. And there will be a normal, like this is a normal at that point. Now, what will happen? It is moving from denser to rarer medium. So it will move away from the normal and it will move away from the normal, something like that, like this. Now, if I increase the angle of incidence, then a particular angle of incidence, or you can say at particular angle of incidence, this angle of refraction will become 90. This angle of refraction will become 90. Like this. So this angle of incidence at which angle of refraction becomes 90 is known as critical angle and is generally denoted by theta c. So what is critical angle? It is the angle of incidence at which angle of refraction becomes 90 degree. Is it clear? And when it happens, when ray is traveling from denser to rarer medium. So one thing is clear, that ray must be traveling from denser to rarer medium. Another thing, angle of incidence becomes critical angle if angle of refraction becomes 90 degree. Clear? Now, what is the expression for critical angle? We can use Snell's law for that, and you know how to use Snell's law. According to Snell's law, if I apply Snell's law, what is it? I have told you refractive medium into sine of the angle, that is mu2 sine theta c is equals to refractive index of this medium, that is mu1 into angle in this medium, that is sine 90. You can say sine theta c is equals to mu1 by mu2. Now, in this chapter, whenever there is a two medium, mu1 and mu2, in that situation, we have to remember it in different way. Like in this method, in this way, mu1 is the rarer medium and this is the denser medium. So the way I recommend you to remember this sine theta c is sine theta c is equals to mu of rarer medium divided by mu of denser medium. In this way, you can easily remember and will never forget where to put mu1 and where to put mu2. What is mu1? What is mu2? It will be resolved. Sin theta c is equals to refractive index of rarer medium divided by refractive index of denser medium. Is everything clear in this scenario? Moving further. Moving further, if I move further, there is another concept that is TIR, known as total internal reflection. Now, this is again a very simple concept. Let's suppose there is a medium. Once again, the similar medium mu1 and mu2. This is the normal, I suppose. Now, I am considering a ray. If the angle of incidence, this is the angle of incidence I. If this angle, I am writing here, is more than theta c, then the ray is reflected back in the medium. Then the ray is reflected back in the medium. And this phenomena is known as total internal reflection. Actually, there is a transparent medium above. Both the mediums are transparent. But still refraction is not taking place. Only reflection is taking place. That's why it is called as total internal reflection. All the light that strikes the media is reflected back. That's why there is a term comes as total internal reflection. Now, what are the conditions for TIR to happen? First condition is angle of incidence should be greater than theta c. What is theta c? Critical angle. And second condition is ray must be passing from denser to rarer medium. This is a very famous condition in which students might get confused. Why it is important? Most of the times the objective question came with a option like TIR will take place or TIR will not take place. So TIR will take place is decided by these two conditions. First condition is angle of incidence should be greater than critical angle, and second condition, ray must be traveling from denser to rarer medium. Till now everything is clear. Now there are various applications of this TIR phenomena. One very famous phenomena is your mirage effect. Just remember the names. Mirage effect. Applications, I am telling you, applications of this TIR. Remember the name. Most of the time they ask you. One very famous is mirage effect. Do you know what is mirage effect? Have you heard about it? The imagination of water in desert. Okay, very good, Lokesh. Second phenomena is 90-degree or 180-degree reflector prism. Third, you can say optical fiber. Optical fiber. Another is the brilliance of diamond. Diamond, I think everyone knows. There is a sparkling brilliance in the diamond. It sparkles like you can say, very brightly. So what is the cause of that brilliance? What is the cause of that sparkling brilliance is TIR. So just remember the name. Sometimes it is asked. Moving further. Now, what is optical fiber? Let's go about it in little bit of details. Optical fiber cable. Listen to me very carefully. This white portion is called as core. This is a cylindrical portion made of quartz or glass with small pieces. Next portion, next layer, this green layer is called as cladding. and this is jacket or protector. You can say plastic jacket to protect it from the damage. Now you understand what is optical fiber cable. There are three components. One is core, another is cladding, another is plastic jacket. Now out of which this core is made of transparent glass and this cladding is also made of some transparent media. Two things are clear. Both core and cladding are transparent. However, the plastic jacket is non-transparent. Now what happens? Let's suppose this is the axis of the cable. When light enters the media, enters the glass like this. Let's suppose light is entering from this. It bends towards the normal. And after reaching this point, both the mediums are transparent, so light should go out. But due to TIR, it just reflects back and travels like this and comes out. Now you can clearly see that TIR is happening at all the interfaces of core and cladding. So one thing I will ask you, which of the medium, core and cladding, will have higher refractive index? This is refractive index of core. This is refractive index of cladding. Which is more or which should be more for TIR to happen? Which should be more for TIR to happen? Anyone? Anyone? Core should have high refractive index. Okay, Gauri Lakshmi is saying core should have. Okay, listen. Very good. Light is traveling. TIR will happen only when light is traveling from denser to rarer medium. That means denser to rarer medium. That means this cladding should be rarer as compared to what? Core. So cladding should be rarer. That means refractive index of cladding should be slightly less than the refractive index of the core. So this is the punchline that you should remember. Now moving further. There is a question based on it. This is a basic question. You should answer A, B, C, D very quickly. Question says, in TIR, when the angle of incidence is equals to the critical angle, what will be the angle of refraction? Okay, answer very quickly. When angle of incidence is equals to the critical angle, what will be the angle of refraction? A. Everybody is saying A. Very good. This is a simple basic question that is based on the concept that I have told you, that angle of incidence is critical angle, then angle of refraction will be 90 degree. Very good. Next question. This is a good question. Now listen to me. Very good, Veena. Now if we move further, question says, a disk is placed on a surface of pond which has a refractive index 5/3. Okay. A source of light is placed 4 meters below the surface of the liquid. The minimum radius of the disk needed so that light is not coming out is. Okay. How many of you were present in the test paper discussion of the last test paper discussion? How many of you were present? Because this is the question based on that only. Let's suppose this is a pond something. This is pond. Clear? Okay, they are saying that there is a source of light placed 4 meters below the surface. That means there is a point source of light placed 4 meters below the surface. That means this distance is 4 meters. This is the surface of the pond. This is the bottom of the pond of 4 meters below the pond. Now what will happen? Nobody was present in the test discussion. From this light source, various lights rays will come. like this way. This, this, and various light rays will come out from this source. Now, imagine one thing. I will draw the diagram again. Just consider one thing. For this ray and for this ray, can you see that angle of incidence is increasing? If angle of incidence is increasing, then one thing is sure that at a certain angle, this angle of incidence will become equal to the critical angle. And if it becomes equal to the critical angle, then ray will not come out. It will just graze like that. And after that, rays will come like that. So can you imagine one thing, that not all the light rays will come out of the water surface, come out of the liquid surface. Why? Because at a certain angle, the rays will start moving back to the water. Why? Due to the TIR. So this question is generally based on TIR. So now I will redraw the diagram. Okay. Now, let's suppose this is the point source. This is the light ray which is going straight. It will not refract anyway because angle of incidence will be 0. Now consider another ray. Let's suppose this ray is striking the surface at a critical angle, which is theta c. So this ray will graze like that. And all the rays inside it will come out. All the rays inside it will come out. Similarly, this thing can happen on this side as well. Now, again, you can imagine that this phenomena should be happening in all directions. I have drawn right and left only, but it should be happening in all directions. So the light rays coming out of this pond will form a circle. Will form a circle, and this circle is known as circle of illuminance. Circle of illuminance. Now we need to find out the radius of this circle. The radius of this circle is, let's suppose, now listen to me a little bit. Let's suppose, not suppose, this is theta c, then by alternate interior, this angle is also theta c. Clear? Theta c is the critical angle. Refractive index of the water is given as 5/3, and outside is air. Air has a refractive index 1. Now, from critical angle definition, sine theta c should be equals to what? Rarer over denser. Sine theta c is equals to what? Rarer over denser. Rarer medium is air divided by denser medium is 5/3. So that should be 3/5. Sine theta c we know now. Sine theta c is 3/5. Now listen to me. I'm going to do something different here. Listen to me very carefully. Sine theta c is generally what? Perpendicular over hypotenuse. That means the ratio of perpendicular over hypotenuse is 3:5. In this triangle, I am telling you, I am highlighting the triangle. In this triangle, let's see. This is the triangle. In this triangle, this is theta c. So now listen. Can you see that this is theta c? So sine theta c will be perpendicular over hypotenuse. Perpendicular is 3. Hypotenuse is 5. This is 3. This is 5. So the base will be 4. By Pythagoras theorem, base will be 4. Now, given situation says the ratio of 4 is equal to 4 meter. 4 is given as 4 meter. So we have to find the radius. So radius will be 3 is equals to 3 meter. So what is the radius? Radius should be 3 meter. I think most of you are not able to understand what's happening in these two steps. If it is not clear to you, I will explain it one more time. For example, let's suppose, for example, are you clear with that sine theta c is equals to 3 by 5? This is perpendicular over hypotenuse. So this is 3, this is 5, this should be 4. Now, what's happening here? If this distance was, let's suppose, 40 centimeter. Let's suppose this distance was given as 40 centimeter. So according to my calculation, this distance is 4. That means this distance is 4 and it is given as 40 centimeter. And we need to calculate this one, which is 3. So 3 will be 30 centimeter. That's how we approach. Here, 4 is equals to 4 meters. So 3 will be equals to 3 meters. That's what I did. This is the simplest way to solve these situations. Now tell me, what's problem in this? Is the question clear or no? Very good, Logesh. Gauri Lakshmi, very good. Now moving further. Refraction at spherical surface. Till now we were discussing refraction at plane surface. Now refraction at spherical surface. One thing, let's listen. Two kind of spherical surfaces are there. One is concave, another is convex. One is concave, another is convex. Let's suppose this is a spherical surface. This surface is divided by two different mediums. Let's suppose this is mu1, this is mu2. Clear? And out of this, what's given is mu1 is less than mu2. Okay, let's change it. Mu1 is greater than mu2. This is given. Now tell me the name of the surface. What you call it? Is it concave or is it convex? Is it concave or convex? Anyone? Concave. Okay. Convex. Okay. Two different answers are there. Okay. Now listen to me. Whenever you have to name a spherical surface, one, I will say, there is a standard rule that look at the surface from the rarer medium. Out of these two, mu2 is the rarer medium. So look at the surface from the rarer medium and it will look like a concave surface. So what is the basic identification of a surface? Look at the surface from the rarer medium. If I look from the rarer medium, this surface will look like concave. So this is a concave surface. And similar surface will become convex if mu1 is less than mu2. Then I have to look it from this side. Is it clear? So now, sticking to the point, what is the point here? What is the point here? What is the phenomena? How to write the refraction at a spherical surface? Listen to me very carefully. I will write it in the actual way how to write it. Sanskriti, it was not convex. I think it's clear to you now. Refraction medium divided by image distance. The way you should write. I am not writing in mu1 and mu2 in terms of mu1 and mu2. I am writing it in standard form. That is refraction medium divided by image distance minus incidence medium divided by object distance is equals to refraction medium minus incidence medium divided by R. This is the standard way to write this. I think every point is clear. Refraction medium over image distance. How to remember it? Refraction medium over image distance minus incidence medium over object distance equals to refraction minus incidence over R. R is what? R is the radius of curvature. That's we have already discussed in spherical mirrors. Radius of curvature. Now, one more thing. R may be positive and may be negative. R may be positive and may be negative, and this is the sign convention that we have used in case of spherical mirrors. What was the convention? That in the direction of incident ray, distances are taken positive. In the direction opposite to the incident ray, directions the quantities are taken as negative. I think that convention was clear in the previous class, so I will not discuss it here. So this is the formula for refraction at spherical surface. Moving further. Now there are thin lenses. Thin lenses. Okay. There will be two kind of lenses you will see. One is convex, another is concave. I will give you a glimpse of that. This is a convex lens. This this is made of glass which has a refractive index mu. And if there is a surrounding, outside is air. This lens is known as biconvex lens. Generally, it is called as biconvex lens. Clear? Now, similarly, one more kind of lens can be formed. That is, one surface is plane, another surface is convex. This is generally known as plano-convex. Plano-convex. Now, listen to me very carefully. One or two things I will describe here. Let's talk about this biconvex lens. This biconvex lens has two refracting surfaces. This is surface 1, this is surface 2. I have named this surface as 1 because I am assuming that object is placed this side, or the incident rays are coming on this surface. Listen to me very carefully. This is very important thing I am telling you. Out of the two surfaces, which surface is termed as first surface? The surface on which incident rays are striking. So most of the times we assume that rays are coming from the left side. That's why I have named it as 1. Now listen to me again. This surface 1 should have its center here. I think this point is clear. If this is a spherical surface, its center must be here. So this radius is known as R1. And the spherical surface 2 has its center, or its center will be here. This distance is known as R2. Clear? So according to this diagram, R1 is positive and R2 is negative. R1 is positive and R2 is negative. Can you identify this situation? R1 is positive, R2 is negative. Similar thing will happen with this diagram. If I say, again, I am talking about plano. This is again very famous lens. This is surface 1, this is surface 2. Now, in this diagram, you can clearly see that R1 is whether positive or negative. Can you answer if object is here? You can say R1 is positive or negative. Quick, quick. Be very quick. R1 is positive or negative? Positive. So R1 is positive in this situation. Very good, Logesh. Now talk about R2. The radius of this plane surface. What is R2? Most of you will answer that R2 is a plane surface. Can you answer what about R2? What about R2? Okay, let me tell you. The plane surface has, okay, plane surface has infinite radius of curvature. Radius is a part of a circle. Huh? You know that radius is a part of a sphere, part of a circle, but plane surface has is not a part of a sphere. Or you can say generally, if you draw a very large sphere, this is a smaller one, and draw a very small part and cut a very small part, this will look straight. So the radius of the plane curve, plane side is equals to infinity. You should remember this in mind because plano-convex lens is very common in which they will ask you such questions in which you have to use R1 and R2. I think one thing is clear in that. Now moving further for concave lens. Concave lens. One more thing I will describe here. Listen to me. This lens has converging nature. Write down every point. Has converging nature. Now, there is a thing that is to be noted. Again, very important thing. Now, listen. What I told you, this convex lens is of converging nature. Now, there is a situation. Listen to me. This is a lens, which is convex lens, and is placed in a medium. Or you can say there will be a question that a convex lens is immersed in a liquid. Is immersed in a liquid. So that situation I am telling you that suppose this lens is immersed in a liquid like this. Now listen to me. Let's suppose the refractive index of the lens is mu1 and of surrounding is mu2, out of which mu2 is greater than mu1. Mu2 is greater than mu1. What is the meaning of that? That lens is immersed in a denser liquid, in a denser medium. In that situation, its nature will change to diverging nature. So I am writing the punchline. When a convex lens is immersed in a denser medium compared to what? Compared to its own refractive index, denser medium, then it becomes diverging. I am writing very quickly, so don't go with the writing, my handwriting. I think everything is clear in this situation. It becomes diverging. Till now, everything is clear. Now, talking about concave lens, I will not take a lot of time. Concave lens will look something like that. This is biconcave lens. Which surface is 1? This is 1, this is 2. If object is there. So R1 is and R2 is. Can you tell me R1 is negative, R2 is positive? Moving further. Now everything will remain same. This lens is of diverging nature. Diverging nature. And if it is in diverging nature, then one thing for sure, that if it is dipped in the denser medium, then it will become converging. When it will become converging? When it is immersed in a denser medium. Moving further. What is focus? I think everybody knows about focus now. Everybody knows about focus. Say yes or no. What is focus? I think this is a basic thing. You can understand it from the class 12th physics. Now, one thing I will tell you, focal length. For converging lens, focal length is positive. For diverging lens, focal length is negative. I am not writing that for convex lens focal length is positive. Mark my words. I am not saying that focal length for convex lens is positive. No. I am saying focal length for converging lens is positive. Mark my words. Focal length for converging lens is positive and for diverging lens is negative. Let that means when you immersed this lens, convex lens in a liquid, and it becomes diverging. So its focal length will also become negative because it is of diverging nature now. But in this condition, its focal length is positive. Are you able to connect these things? What is the meaning that diverging lens has negative focal length, converging has positive focal length? In this situation, it is behaving as converging, so focal length is positive. In this situation, it is behaving as diverging, so its focal length is negative. Moving further. What is lens equation? This is again a very famous equation. I think everybody knows that 1 over f is equals to 1 over v minus 1 over u. I don't need to explain it. V and U are the terms that were explained in the previous session. Image distance, U is the object distance. All the distances are measured from optical center. Lens maker formula. This is again a very famous situation. Let's suppose this is a lens. This is surface 1, this is surface 2, object is somewhere here. Now, what is lens maker formula? 1 over f is equals to refractive index of lens over refractive index of surrounding minus 1. 1 over R1 minus 1 over R2. This is how we actually write the lens maker formula. I think you have studied it something like mu minus 1, 1 over R1 minus 1 over R2. I hope that you have studied in that form only. But the actual form is mu of lens divided by mu of surrounding minus 1. Lens over surrounding minus 1, 1 over R1 minus 1 over R2. Is it clear? The formula that you should remember. I think I should write mu L is refractive index of lens. Mu S is what? Refractive index of surrounding. R1 and R2 are the radius of curvature. What kind of question generally comes from this? The question that generally came from this is, a lens is placed in air, has a focal length of 20 centimeter. When it is immersed in a liquid of they will say refractive index 5 by 4 or 5 by 3, what will be its focal length? And the refractive index of the lens will be given. Using this formula, you can solve that. Very simple question. Magnification. Again, magnification is a basic term which indicates magnification is height of image divided by height of object. In case of lens, it comes out to be V over U. V over U. Moving further. Remember this formula. There is nothing more in that. Power of a lens. Again, very simple formula. P is equals to 1 over F. The unit of this is diopter. Diopter. And F is placed in meter. Now, generally, focal length is given in centimeters in your questions. So what it will be? It will become P is equals to 100 by F. Now you can put F in centimeters. So whenever you are given a focal length of 20 centimeter, you should use this relation so that you will get power. Clear? The unit is again diopter. Diopter. These are the very small topics, so I will not take a lot of time moving further. Combination of lens. This is again a very important topic. Most of the questions generally come from it. There is a question on the next slide, which involves what is focus. So you have not asked me what is focus, so I'm assuming that you were able to know, you were able to solve that question, because that question is involving focus. The definition of focus is actually involved. So now I'm talking about what is combination of lenses. For example, this is a lens. This is another lens. Two lenses are placed back to back in combination. The first lens has a focal length f1, the another lens has a focal length f2. Then what is the equivalent focal length of this system? The equivalent focal length of this system is 1 over f1 plus 1 over f2. Now, one thing to be clear, that these focal lengths, we have to use sign convention. So sign convention is to be used while applying the formula. You have to put the sign convention. As look at that, this is a converging lens, so its focal length is positive. This is a diverging lens, so its focal length is negative. This focal length is positive. Can you understand that? So whenever you are applying the formula, you have to apply the sign convention. Moving further, there is a question. Read out the question. Read out the question. Question says, a convex lens A of focal length 20 centimeter and a concave lens B of focal length 5 centimeter are kept along the same axis. Okay. With a distance D between them. If a parallel beam of light falling, okay, let's draw it first. Okay, I'm drawing it. There is a convex lens, something like that. And on the same axis, there is a concave lens. And the separation between them is something D. That's given. Okay. Focal length of first is 20. And focal length of second is what? 5 centimeter. Now they are asking, if a parallel beam of light, now draw it, if a parallel beam of light falling on A, this is A, this is B. Let's suppose this is a parallel beam of light falling on A, leaves B as a parallel beam. That means it comes here and leaves B as also as a parallel beam. Then what is the distance D in centimeter? Now listen to me. By the definition of focus, the rays which are passing parallel to the lens, the rays which are passing parallel to the principal axis will meet at the focus. That is sure. That means these rays will meet at the focus for the first lens A. Now, by the definition of the second, of the concave lens, what I say, the emergent ray if I draw it with the similar pen, what's happening? The thing is, the emergent ray will be parallel to the principal axis only when the rays incident on it, are parallel, are coming to meet the focus, Is the point clear what I'm saying? For concave lens, rays will become parallel to the principal axis when they are incident on the focus. That means if I draw this with some different color pen, something like this. Okay. The diagram should be very clear. This lens has diverged the rays, and these rays are meeting at this point. Similarly, these rays are also meeting at this point. Now, the rays coming at the focus will become parallel to the principal axis. So these rays will become parallel to the principal axis. That's the situation. Now, when the rays are coming parallel to the principal axis, convex lens, they will meet at the focus. That means this complete distance is the focal length of the first lens. That means this distance is 20 centimeter. And they are becoming parallel to the concave lens. That means they should reach the focus of the concave lens. That means this distance out of this is 5 centimeter. So the separation between them, this total is 20. This part is 5. So this portion should be 15 centimeter. So answer is C part, that is 15 centimeter. So this question is completely based on the definition of focus, that when a ray will become parallel to the principal axis or when it meet the focus. So this is all depends on the definition of focus. You can ask, otherwise I will move further. There is one more question. This is again a difficult question. I think so. Not so difficult. Two similar thin equiconvex lenses of focal length f each are kept coaxially in contact with each other. In contact, listen, in contact with each other, such that the focal length of the combination is f1. Now listen. These are the two lenses. One and another. I think there should not be a space. There shouldn't be a space. This is another. These two lenses are placed in contact. Both have a focal length f. Clear? And the combination has a focal length f1. So by the combination, by the definition of combination, you know that 1 over f1 is equal to 1 over f plus 1 over f, because both are same focal length. So that means 1 over f1 is equal to 2 by f. That is equation number 1. Now again, what are they saying? They are saying when the space between the two lenses is filled with the glycerine. Now here some glycerine is inserted in this space. Now can you see that the glycerine is forming another lens which is of concave nature? You can see that the lens formed by the glycerine is of concave nature, which has the same refractive index 1.5. This is not m, this is mu, as that of the glass. Then the equivalent focal length is f2. Okay, now listen to me. For the calculation of equivalent focal length, what we know, that we need to put 1 by f, 1 by f, 1 by f1, 1 by f1 plus 1 by f2 plus 1 by f3. So there are three lenses. Two focal lengths are known, f and f. The third focal length is to be calculated. For that, they are saying, if you know the lens maker formula, it says 1 over focal length is equals to mu lens over surrounding minus 1 by R1 minus 1 by R2. Now, according to the question, both, or in fact all three lenses have same refractive index, because it is saying that same refractive index, and all have same radius. all have very good, Gauri Lakshmi. I think you have answered it. C. Let's check whether it's correct or not. All the lenses will have same radius of curvature, same refractive index, so their focal length will also be same. That means third lens will have will also have a focal length f. Now, what we will do, we will again apply the formula of equivalent focal length. 1 by f2 is equals to, this is first lens, this is second lens, and this is third lens. 1 by f plus 1 by f. Now third lens is concave, that is minus 1 by f, because focal length of concave lens is negative. These two will be cancelled, so 1 by f2 is equals to 1 by f. Now we need to divide, you need to calculate f1 by f2. If you calculate that, if you calculate what is f1 by f2, this is equation number second. If we do 2 by 1, then it will be f1 by f2 will be 1:2. You can divide it. You will get f1 by f2 is equals to 1 by 2. So 1 by 2, if you talk about which option is correct out of these, I think very good, Gauri. Right now, Gauri. Okay, Gauri Lakshmi, very good. You got the correct answer. That is 1:2. Very good. Now there is one or few more concepts are there. Another concept is cutting off lens. This is to be remembered actually. This is a lens. Let's suppose this is a lens which has a focal length f. Now it can be cut in two ways. One is it can be cut along the principal axis or parallel to the principal axis like this. So the two pieces will be formed like that. I am not an expert in drawing. So two pieces. All these two pieces will have same focal length. All these two pieces will have the same focal length as the original lens. So what is the thing to remember? When you cut the lens parallel to the principal axis, like you can cut it along any of these lines, along this point, but all these cutting is parallel to the principal axis. In that situation, focal length will not change, or you can say focal length will remain same for each part, remain same as to the original lens. Now, another concept is you can cut the lens. This is a lens. You can cut the lens perpendicular to the principal axis like here. From here to here. You can cut the lens in two equal pieces. If you done so, then focal length of each part, like each part will be something like that. This is a plano-convex lens, and another part will also be a plano-convex lens. And both the parts will have a focal length double the original focal length, that is 2f and 2f. Keep it in mind, the original focal length is f. So the lens is formed by cutting perpendicular to the principal axis will have twice the focal length of the original lens. That is 2f and 2f. Keep this in mind. Most of the questions will come from that. Keep it in mind. Moving further. Now refraction through prism. This is again a very important topic. I think the last topic before optical instruments. Let's suppose this is a prism. This is a prism. Let's suppose this is A, B, and C. One thing you should know, let's suppose this is a ray which is incident on the one face of the prism. At this point, there will be a normal. This is the normal. This ray will refract towards the normal, like this. And if I draw a normal again, this ray will come out, and now this is moving from denser to rarer moving, so it will move away from the normal, something like that. Now there are few angles you should remember. This is called as angle of incidence I. This is called as angle of emergence E. Remember each word. This is first angle of refraction inside, that is R1. This is angle R2. Now, in this diagram, the angle made by the faces in which refraction takes place is A. And this A is known as angle of prism. Angle of prism. Listen to my word very carefully. This is known as angle of prism. Now the relation, one more thing that you should remember. Can you see with this pen? There is one very common thing. What is delta? Angle of deviation. The actual incident ray is moving in this direction. This is the actual ray. Now, finally, it comes out in this direction. So the angle made by the incident ray and the emergent ray is known as delta. This is angle of deviation. And you will get a relation for this delta. Delta is equal to I plus E minus A. This is a very golden relation. Delta is equal to I plus E minus A, where I is the angle of incidence, E is the angle of emergence, A is the angle of prism. Till now, everything is clear. Now, one more thing to be important, to be very important here, the graph. I think there is only one slide for us. So I will do a little bit, I will say congested things here, but you should draw it on your notebook. Another thing is graph between delta and I. Delta and I. Delta is angle of deviation. Write it, delta is angle of deviation. If we draw a graph between them, it will look something like that. It will look something like that. So you can see here that as the angle of incidence is increasing, delta is decreasing, and after that delta starts increasing. That means delta has a certain minimum value. At this point, delta has a certain minimum value, and which is known as delta minimum. Minimum deviation means delta minimum. What are the conditions? For delta to be minimum, what are the conditions? That is, I is equals to E and R1 is equals to R2. Clear? I is equals to E and R1 is equals to R2. This is when delta is minimum. Now, one more thing, one more relation that you should remember. Index of this glass prism is mu. So the final relation that I will tell you, golden relation, mu is equals to sine divided by sine A by 2. This is the golden relation that you should remember. I will send you the PDF form of this slide so that you can solve or read the remaining part. Will be some PYQs, so I will not take a lot of time that you can. So ending the session now.